Vivek Korode sir, who invited me for this STTP. So we'll start. Today's my topic is the application of carbon nanotubes, a DFT study. So we know nowadays nanotechnology is emerging field. So there are two parts, nanoscience and nanotechnology. So where we are going to apply the applications, all these nanotechnology into the various fields like medical, science, engineering, and everywhere in our day-to-day life. So we'll start first with the basic. Uh, what is nanotechnology? So nanotechnology, as we know, the process of engineering material at atomic scale, very small scale, that is called a nanoscale or molecular scale. So it is the field of science that manipulates matter on a near atomic scale to design what is the application. So design new structures, new materials, or new devices that are few at nanoscale dimension. So nanotechnology is crucial for the progress and evolution of all scientific disciplines, such as medicine, manufacturing, energy, material science, and engineering. So, yes, sir, I'm not able to change this slide. Let me take it again. This is my outline of the talk. Okay. So we'll start with the nanotechnology. As you know, this nano word is taken from the Greek word nanos. So the nanos, meaning of nanos is extremely small. So as we know, 1 centimeter scale is 10 to the power minus 2 of meter. Then 1 micrometer is 10 to the power minus 6 of meter. Whereas nanometer is 1 billionth of meter, that is of the order of 10 to the power minus 9 meter. Okay. So hence all nanoscale structures or nanomaterial typically have dimensions within this range. You can check the dimension. 1 nanometer to 100 nanometers. Okay, so these are the few examples of nanomaterials. That's fullerene, liposome, dentimer, carbon nanotube, and graphene. Okay. So here in this nanoscale, basically used to study the atoms and molecules. At that we are going to study it in atomic and molecular level. So we are going to deal with the single atom and molecule, okay, or the clusters or the few clusters means combination of few atoms and molecules. Okay. So as per the key observations, material with at least one facet means maybe a length, maybe a breadth, or a length, or a height that is in the range of 1 nanometer to 100 nanometer. These are known to be a nanomaterials. So at this level, at the nano level, the material tends to reveal a distinct physical chemical properties compared to the same material at a microscope capacity. So at this nano level, this material shows different properties, okay, than the macro level. We can take an example of silver material. If we break the silver material into smaller proportion, each piece shows the properties like density, its texture, its boiling point, its thermal conductivity, just like a original silver. But if you cut it, or if you go to the nanoscale, that is silver nanoparticles, okay, very small particle, then their size, their shape, their composition, that it shows a different properties than the macro level. So all properties get changed at a nano level. A simple example, another that you can consider the gold material. It expects different colors at different nanoscales, different nano dimensions. Means 1 nanoparticle, 5 nanometer, 50 nanometer, 100 nanometer. At each level, it shows different colors, as well as it shows different catalytic properties that vary according to the material size for these gold nanoparticles. There are the very famous two examples that is of the nanoparticles, and each has have a different applications at nano level. Now, how to deal with these nanoparticles? So, the as we know, initially the observation started with the electron microscope, which was introduced in 1931, and but it shows only the microorganism, not nanoparticles. So later on in 1981, the first device is introduced which can give you the image at nanoscale. That is what the scanning tunneling microscope. Okay. That is called STM. Then after that, SEM, scanning electron microscope, then transmission microscope, also discovered for further detailed study of the nanomaterials. So the additionally small size of nanoparticles allows them to be easily incorporated into wide variety of products, processes, including electronic devices, medical treatment, energy production, and environmental remediations. Properties of nanomaterials also make them useful for creating a new product and improving existing ones, such as increasing the efficiency of solar cells and batteries, creating stronger and more durable materials for construction, and developing more effective medical treatments like cancer and all. Okay. So these are the introductory part of this nanomaterial nanotechnology. Let's go in little bit detail on it. So very famous material is carbon, which is one of the most plentiful element on the planet. It is found in nature as a graphite, diamond, and coal in its basic form. So due to their unique hybridization characteristics and their susceptibility to perturbation during synthesis, the nanostructure allotropes forms of carbon have been extensively studied over the last few decades, allowing the precise modification of a material properties. So there are various hybridization states of the carbon: chemical, mechanical, thermal, electrical. These characteristics of various allotrope forms are closely connected to their structure and hybridization state, allowing the same material to be used for the varieties of applications. So here you can check in this diagram. Uh, we start with the zero dimension material. So you can check over there is a fullerene material, then onion-like carbon, carbon dots, graphene dots. Okay, these are the zero dimension nanomaterial. Then the one dimensional material are carbon nanotubes. That again the types of single wall, multi-wall carbon nanotubes. Okay. Then carbon nanohorns as well. Another the combination of carbon nanomaterial. Then the two dimension is graphene. Okay, and that is derived from the graphite material. And three dimensional material is the diamond or a graphite. Okay, that is a well-known structure. So these are all allotropes of the carbon. Okay, just little bit introduction about each allotrope, and then we'll move to the carbon nanotubes. So first we'll talk about the fullerene. It is also called Buckminster fullerene, C60. Okay. So the fullerene is not only C60, it may be a C20, then C30, okay, C42 and all. So this is what the carbon allotrope discovered in 1985 by the scientists Curl, Proto and Smalley. Okay, they published their paper in 1985 regarding the discovery of fullerene. So carbon atom makes up fullerene molecules which are hollow sphere, ellipsoid, or it may be a tubular. So Bucky shape of spherical fullerene are also known as buckyballs. So enormous curvature of these hollow spheres, conjugated electron system enables rich chemical behavior, permitting the synthesis of wide range of derivatives. Making the fullerene family a useful building block, fullerenes are insoluble in nature, thus their biological applications are ongoing interest. Fullerene family, especially C60, offers attractive photographic, electrochemical, physical properties that can be used in several medical fields. Fullerene derivatives, these are also used in the HIV treatment, contrast agent for magnetic resonance imaging, antioxidants, antibacterial agents, and they're also useful as targeting vectors to mineralize the bones, sensitizer for photodynamic therapy. So these are the just the few of the applications mentioned over there for the fullerene. And then we'll move to the nano diamonds. That is another zero dimension material. These are the carbon nanoparticles that are typically around 2 to 8 nanometer, very small in size, in the diameter with the truncated octahedral architecture. Generally, the surface of nanodiamond is coated with a layer of functional groups that stabilize the particle by reducing the dangling bonds. So conversion of sp3 hybridized carbon with sp2 also results in the increasing stability of the particle. Chains and graphitic patches are formed by the carbon in sp2. Oxygen containing groups end the majority of surface atoms, and some nanodiamonds are faceted, whereas most have rounded shape. So synthesis of these diamonds, that is nanodiamonds, is relatively affordable and despite their extreme high cost. So selective use of nanodiamonds, on the other hand, necessitates the specific photochemical characteristics, additional surface modifications with various functional groups. Then the study of the nanodiamonds, that is what the disaggregation, physiochemical characteristics, surface modification, biocompatibility, fluorescence, and optical dispersion. These studies have developed a broad perspective for these biomedical applications. So though there are various properties such as ability to load a high amount of drugs and ability to penetrate cellular membrane, these diamonds have shows tremendous potential to emerge as medium for transporting drugs into biological systems. And the innovative properties of this biomaterial have revolutionized various drug delivery systems, supporting gene delivery vehicles and identification of biomolecular targeted drugs. Then we'll move to the carbon quantum dots. These are the kind of carbon nanoparticles with a size less than 10 nanometers, around the same size as diamonds. It have been focused research because of their fluorescent, non-toxic, water dispersible properties. So at high temperature and pressure, it can be made from graphene, cellulose, or other materials. Due to their unique properties, it have received much attention. So these carbon quantum dots are fluorescent carbon nanostructure with two origins of fluorescent properties: emission of fluorescence from conjugated pi domain band gap phases and fluorescence from the surface defects. Various elements such as nitrogen, sulfur, and phosphorus have been used in doping the carbon quantum dots to improve their properties. So functionalization can be done for this carbon quantum dots. They also help in reactive oxygen species through hydroxyl free radical, leveraging properties of doped ions and photoluminescence by increasing their fluorescent brightness shifting and their emission spectrum. So from biological imaging to electrical photonic devices, these quantum dots brings up a new possibility. Carbon quantum dots are notable for being constructed out of plentiful and largely harmless element, which can aid the ecological responsibility development of a solar technology. In the near infrared spectra area, carbon quantum dots can emit fluorescent, making them ideal for biological applications. They have benefits in various sectors such as biomedicine, solar energy conversion, photocatalysis, light emitting diode, photosensors, and also used in delivery of DNA and cancer treatment. Then the very famous structure is a carbon nanotube. So these carbon nanotubes have introduced by the scientists Ijima and Ichihashi in 1993. Okay, so this commonly known as bucky tube, and these are a carbon-based nanoscale hollow tubes. Aspect ratio means length to diameter value of these cylindrical carbon molecules are generally more than 100. So these nanotubes are classified as single wall carbon nanotube, multi wall carbon nanotube. It is also categorized in different ways like armchair carbon nanotubes, zigzag carbon nanotube, and chiral nanotubes. Now, how this can be synthesized? There are different methods to use to synthesize the carbon nanotube, like laser ablation, high pressure carbon disproportion, chemical vapor deposition method. And this CVD method has been most widely used due to its high yield capacity. So carbon nanotubes obtained using this method a high degree of length, and its morphological characteristics are more enhanced. So about the carbon nanotubes, we are going to discuss it more detail in the few next slides. Let me introduce one more material, that is what the graphene. Okay. Graphene is what the another allotrope of carbon. This is two-dimensional material. It is made up of single sheet of atoms organized in honeycomb lattice in 2 dimensions. So the name combination of graphite with the suffix "in" that it refers to graphite allotropes of carbon, which is made up of stacked graphene layers. So graphene is two-dimensional sheet which is of sp2 hybridized carbon atoms organized in hexagonal lattice. So it has gained traction among the both science and technological communities to its mechanical, electrical, and thermal properties. The structural flaws are introduced into the lattice during the growth or by physiochemical treatment, which can dramatically impair the graphene's characteristics and result performance of graphene-based device. Melt intercalation, in situ polymerization, solution mixing are the most common techniques for incorporating graphene into the polymer matrices. Recently, there has been significant progress in the creation of a graphene derivatives such as graphene oxide, porous graphene, or graphene reduced graphene oxide. Okay, so another important kind of graphene is the zigzag pattern found in the structure of graphene, uh, commonly called nanoribbon of graphene nanoribbon. So this is all about the introduction of few of the allotropes of a carbon. let's try to understand the structure of carbon nanotube. Okay. So here you can see the schematic of two-dimensional image of a graphene sheet. Okay. So it is just like a honeycomb structure, and this is used to understand the carbon nanotube structure. We can use this image. Okay. So here it's mentioned like CH is equal to Na1 plus Ma2. So A1 and A2 are the basis vectors. A1 and A2 are the basis vectors of this, and N and M are the integers, which forms the different types of carbon. So, so to understand this structure, we'll just wrap this graphene structure. Okay. Just from this point, we have a sheet, and we're just going to round it up. We're just going to wrap it from. We are just going to touch this point with this one. Okay. For this, it forms a zigzag nanotube. So if M is 0, we have CH. CH is called chiral vector. Okay. So CH is equal to Na1, where M is 0. So we have only Na1. So just in that case, we have only A1 vector, and this point we are just going to overlap with this point. Okay. So n is the number of vectors. So 1, 2, 3, 4, 5. So for example, 5. Okay. So we just have 1, 2, 3, 4, and 5. So we just put this dot over there, this point over there. So it forms a zigzag type of nanotube. Okay, like this. So n0 is what n is an integer, which is maybe 2, 3, 4, 5, 6. Okay, that will give you the zigzag nanotube. Then the another kind of nanotube, that is armchair. Okay. So I'll show it in the next slide. So in first case, if you overlap, okay, we just move along the vector A1 where M is 0. Okay. So we'll get this type of nanotube. Okay. This shape will be like this. Along the dimension, we have zigzag shape. So it's known to be a zigzag nanotube. Okay. And if you consider armchair nanotube, armchair means we'll instead of this point, okay, we'll just wrap it in the another pattern. Okay, we'll just this we'll just wrap this point with this point. Okay, so that is what the armchair nanotube. So they can check, it can be seen like an armchair. This shape. So that shape can be clearly seen. So this type of nanotube is known to be armchair nanotube, and the last one is the chiral nanotube. So you can put this point, okay, this point you can put anywhere on this, okay, except this n is equal to m or m is equal to 0. Any other possibility that forms a chiral type of nanotube where n is not equal to m. Okay, so all these three type of nanotube will show the different properties. Okay, so if you wrap or if you roll a two-dimension nanotube, that will give you the uh, uh, carbon nanotube. So in that, the length for carbon nanotube, the length is in few nanometers, and the diameter is length is, let's say, around 100 nanometer, and the diameter is only around 5 nanometer, and so on. So that's why it is known to be a one-dimensional material. So the what are the properties it can show? So armchair nanotube, it seems to be a metallic. Okay, it shows the metallic properties, and if with the condition that for a n minus m is equal to 3k, means 3 or 6 or k is like an integer, 3, 6, 9, then it shows the metallic properties. And if it is not equal to 3, the difference of these two vectors is not equal to 3, then it shows the semiconducting properties. So depending on the wrapping structure, so it forms a chiral, armchair, or zigzag nanotube. They will show the different properties in this case. So armchair is metallic in nature, and chiral may be a metallic or maybe a semiconducting based on the difference of two vectors, that is n and m. So these are what the three basic types of nanotube. This is what the image, that is what the STM image observed by odometer and published in 1998. So just here you can clearly see the honeycomb lattice structure, and that is a wrap in the tubular form. So that is what the image of carbon nanotube. So these are the various applications. So use as a storage material, can be used as a gas absorbent, electrocatalytic electrode, conductive film, nanocomposite, biosensors, and various applications in medicine. So in uh, today's talk, we are going to discuss about the uh, storage property, and that is adsorption property. These both, yeah, hydrogen adsorption and different gas adsorption on the carbon. So okay. This is what the uh, initially we have started our work with the graphene. Okay, we uh, tried to adsorb the hydrogen atom or hydrogen molecule, not atom, hydrogen molecule on the graphene. Okay, but the pure graphene is not able to adsorb that. Is the adsorption uh, binding energy for that graphene hydrogen is found to be very less. So then we shifted to the carbon nanotubes, and in that carbon nanotubes, again, if you use a pure carbon nanotube to adsorb the hydrogen molecule, then it shows very less binding energy. So we want to improve at that time the binding energy of hydrogen. Okay, so we used this few dopant, means there is a functionalization. The functionalization can be achieved by different ways. Now we have used the functionalization by alkali alkali metals like sodium, lithium, and potassium. Okay. So all these alkali metals first adsorb on the carbon nanotube. So this is what the one type of functionalization. Now another type of functionalization means the modification carried out on the carbon nanotube to uh, increase their properties, adsorption properties. It can be done just by doping. Instead of keeping the this atom, that's just this is what the sodium atom. Instead of placing on the surface, we can replace one of the carbon atom with that. That also we have done, and that we are going to discuss that one. Now in this diagram, we want to improve the adsorption properties of this carbon nanotube just by attaching the sodium atom on top of it. So what are the possibilities? We have tested all the possibilities that one may keep this sodium atom on the top of this carbon atom. That is called T. T is mentioned over there. That is what the top side. So we tried to keep the sodium atom on top of this sodium atom, and then we submit the job, the process for the geometry optimization. Okay, so let me tell you geometry optimization. Now this study we have done on the software called Material Studio, and we have used the castep to run the program. So this Material Studio or Quantum Espresso or Win2K or Gaussian, these are the different softwares which are available, or the codes which are available, which runs on the basis of density function theory. Now we are not going in details of what is the density function theory and all, because it required another session for it. So this is what again there is a deep study of density function theory. We are just taking the help of that density function theory to learn our system or to carry out our research. So here in this case, we have modeled this system with help of software called Material Studio. That at the end I will show you how to model and all. So now we just try to understand what is modification done over here. So here we place a sodium atom. This the purple color atom is the sodium atom, and the green color atoms are the carbon atoms. So this is what the 80 carbon atom. So again, it is a armchair type of nanotube 80. So we can have 30, 50, 80, 10, different types of nanotubes. So as the number n increase, the diameter of the carbon nanotube will increase. Okay. So we have chosen this 80 only because we have already different types of CRT, but I am showing you to 80 carbon nanotube is easy to synthesize as per the other, as compared to the other carbon nanotube. So in this, we are going to attach this sodium atom on this hexagon. Okay. So one of the possibilities top surface exactly on top of the carbon atom. Another along the bond of this carbon atom denoted by C. So this place on the these two between these two carbon atoms, and this is what A. A is the axial side. So we can say like this is what the axis of a carbon nanotube. It will be like this axis. So this is known to be axial axis. This is what C stands for chiral, T stands for top, and H stands for hexagonal center. Okay, at the center of hexagon. So we tested T, C, A, and H, or four possibilities, and in which the H side means this is the structure shown in the second diagram. This is found to be most stable. Most stable means out of these four, the binding energy is found to be minimum. The energy is found to be minimum. So whenever we can say the atom is in ground state, means the energy is minimum. That is we can say this the most stable structure. So out of these four, the center at that the atom sodium atom placed at the hollow position or the center on top of the hexagon, at the center of hexagon, found to be a most stable structure. Now, what is the distance between this carbon atom and sodium atom? Is around 2.5 to 2.7 nanometers. Okay, here mentioned 2.7 and 2.5. These are the minimum and maximum distance between sodium and carbon atom. As this distance is not same because this is what curvature in shape. No, carbon atom is curvature in shape. So this is at closest distance. This is at longest distance. So minimum distance 2.5 nanometer and maximum distance 2.7 nanometer. This is what the choosing of adsorption site for sodium atom. And after this, we are going to uh, we are going to attach the hydrogen atom, or we'll try to adsorb the hydrogen atom on this system, on this sodium carbon nanotube system. Okay, Na attach 80 carbon nanotube system. Okay, so it's not only sodium, we are also tested for potassium and lithium. Okay. And about the nanotubes, near about 6 different types of nanotubes we tested over there. Here, uh, that is chiral type of nanotube, SWCNT. Then SWCNT stands for single wall carbon nanotube. We have a multi-wall carbon nanotube or single wall carbon nanotubes. Here we have used only a single wall carbon nanotube. So this is what the 33 SWCNT. Another one is 42 SWCNT. On each structure, we have tried to attach the sodium atom to what modify the adsorption properties. We want to increase the adsorption capacity for the hydrogen on this carbon nanotube. So we just functionalize it just by doping, not doping, just by attaching the sodium atom on top of it. So the figures, that is 2.7, 2.5, this is what the range. Sometimes it may be a 2.4 or 2.8 bond length, that is between sodium and carbon nanotube. It may vary because the arrangement for each carbon nanotube, maybe a chiral, maybe zigzag or armchair, is different. That's why there is a little bit variation in this. And also there is a variation in the binding energy. Okay, so it's mentioned EB is minus 1.54. This is what the binding energy of a sodium atom. So that can be calculated just by the binding energy of total system minus binding energy of the pure carbon nanotube and binding energy of sodium atom. So that will give the binding energy for uh, this sodium atom on this carbon nanotube. So it is varying from minus 2.51 to the minimum is minus 1.5. So minus 2.5 to minus 1.5 is the range of binding energy for all different types of nanotubes. So, uh, but in detail, we studied this 80 carbon nanotube. Okay, we also tried other as well, but this is what the 80 carbon nanotube on for hydrogen storage. Here, the binding energy for the sodium is found to be minus 2.05. Okay. And with this, there is this kind of structure. This is what just like we dope here, the attach here the sodium atom on top of each carbon nanotube. Similar work can be carried out for lithium and potassium, that is shown over here. And this is the diagram which is where the potassium is attached on top of 80 carbon nanotube and with also one hydrogen molecule. Okay, so first we attach the single potassium atom on the carbon atom, and then we try to increase the number of hydrogen molecules on top of it. So this is one hydrogen atom which is adsorbed on this at a distance of 2.64 from what, from potassium. So distance between potassium and this the hydrogen molecule is 2.64. Now we just keep adding the number of hydrogen molecules. Here we have added two hydrogen molecules, three, and then 4 and 5. This is what the maximum possibility. This structure, that is 80 SWCNT with potassium, it can absorb maximum 5 hydrogen molecules. Okay, so this what kind of adsorption? It is a Peace option. Okay, not Chemis option over there. So similarly, we have also studied the lithium. Okay, and in each case we have studied bond length, we have studied bond angle, we have studied binding energy as well. So here the lithium instead of sodium or instead of potassium, lithium is attached on this carbon nanotube, and on top of it one hydrogen molecule, then two hydrogen, three hydrogen, 4 and 5. Maximum 5 hydrogen molecules can be adsorbed. So we are trying to increase the capability. Okay, but so with the help of lithium or sodium or potassium, we try to increase the adsorption capacity. If we have only pure CNT, that is called pristine CNT, whether 80 or 50, 33 or 55, it can adsorb maximum 3 hydrogen molecules. But here potassium and lithium can adsorb 5 hydrogen molecules. An interesting thing is that if you try to adsorb hydrogen molecule on uh, sodium, that is sodium attached 80WCNT, it has adsorbed 6 hydrogen molecules. Okay. So uh, the adsorption capacity for the hydrogen on this CNT has increased from 3 to directly 5. So here maximum 6 hydrogen molecules can easily be adsorbed on this sodium attached carbon nanotube with the variation in the bond length from around 2.4 to 2.3. That is what bond length between hydrogen and sodium, and the bond length between sodium and carbon is around 2.8, 2.7. Okay, so that we already discussed in earlier PPTs. So this is what the structure we have. Now what is the diameter of this? Is diameter of this CNT is around 3.3 angstrom, and the diameter will vary if you change the number. Like if you have 50, then it's come around 2 point something. Okay, and if you have 10, then diameter will increase. So because the number of atoms will goes on increasing, the diameter will increase. So this is the very small structure, but not small. This is what a medium nanotube that we choose, 80 WCA for the absorption of carbon. Now this is what the few key observations from that. So this table is giving the bond length between the carbon and sodium, and sodium and hydrogen. Okay, so 6 hydrogen molecule easily adsorb on this sodium attached carbon nanotube. Okay, and these are the if you keep increasing hydrogen molecule 1, 2, 3, 4, 5, 6. Okay, there is no as such change between carbon and sodium bond length. The bond length is varying from 2.50, that is what the minimum, uh, and maximum is 2.7. 2.7 to 2.8. These are the different bond lengths. Okay, why the bond lengths are maximum minimum? Because the curvature nature of the carbon nanotube. Okay, but if you have graphene, okay, and if you are going to dope the going to attach sodium and the plain graphene sheet, then all the bond length will be same. Okay, so this change is only because of the curvature of the carbon nanotube. So if we have a curve, okay, instead of graphene, we have curvature in carbon nanotube. So we'll get a more surface area. That's why the surface to volume ratio is found to be more in case of carbon nanotube, and more hydrogen atoms can be adsorb or attach on the carbon nanotube. So this is what sodium to hydrogen bond is varying from 2.3 to 2.4 for minimum and maximum also 2.4 to 2.5. So this summarize the all bond length from carbon to sodium and the hydrogen to sodium. Now, apart from this, what kind of characteristic have been studied? So this is what they TDOS, that is what the total density of states. Okay, that can be calculated. This is what one of the electronic properties. We have calculated total density of state and the charge transfer on this particular structure. So these are the, you can clearly see this orange color plot is of CNT. Okay, so this is what the total density of state for pure H0SWCNT, and below one, that is in purple color, that is what sodium doped SWCNT. So before doping, that is what the for crystalline CNT we have this kind of density of state. Now here, what is this dotted line? This is what the Fermi level. Okay, so this is what the states below the Fermi level. These are the states above the Fermi level. Okay. So if you dope the carbon nanotube, there is a little bit modification you can see. The whole graph gets shifted by some amount. This is around 0.8 EV electron volt. So if you attach the carbon nanotube on attach the sodium on carbon nanotube, then after the modification, after the functionalization, the plot gets shifted toward left hand side below the Fermi level. Okay, this is what just above the Fermi level, but it gets shifted to the, this is what the after adsorption of sodium atom. So there is a shift in this the graph, that is what in the density of state. And what happens if we dope the hydrogen molecule? If you try to attach or try to adsorb the hydrogen molecule on sodium, that is CNT Na. Okay, WCNT Na. So the another graph is partial density of state. In total density of state, we cannot segregate where the densities of s orbital, p orbital, or d or f, whatever. But in partial density of state, we can check individually whether it is 2p orbital, 3s orbital, or 1s orbital. We can individually check what is the density over there. So here these hydrogen bonding orbitals, here we can around 9.5, there is a peak for this hydrogen. This first one is for carbon, and carbon ka 2p orbital, and this blue one is sodium 3s orbital, and this 1s orbital of hydrogen. Okay, so here you can check there is a peak at 9.5, which is far below the entire carbon 2p orbital, because carbon 2p orbital is having peak somewhere here, but this is there is no matching at all over there. Hence, there is no further lowering of carbon 2p eigenvalues as compared to the SWCNT system. These are the conclusions from this total density of state and partial density of states. Another electronic property we studied for this system is charges. What are the charge? How the charge transfer from this? So electronic charge transfer has been studied using the which method? That is Hirschfeld population analysis. There are two types of analysis: molecular population analysis and Hirschfeld population analysis. So here we can check the charge on each atom. Okay, here sodium, the charge on it is plus 5, 7, and if for each carbon atom 0.049, 0.027, if you move away from it, the charge goes on decrease, move away from the sodium atom. So when first hydrogen molecule adsorb on NaSWCNT, the charge on Na reduce. Earlier it was 0.579, but if you try to adsorb the hydrogen molecule, this is what the hydrogen molecule, the charge gets reduced from 0.579 to 0.50. Okay, a little bit change in the reduction in the charge. So charge here after H2 adsorption, the charge goes reduce. Okay, so ionization of sodium atom takes place here at the adsorb on the SWCNT, and it carries 0.79 charge. And if you adsorb the hydrogen molecule, so due to the polarization mechanism, the 2 nearest and 4 next nearest carbon atoms are negatively charged. With 0.049 is 0.049 is nearest atom, and 0.27 that is next nearest atom, 27 and 0.26. These are the charges on each carbon atom, which are nearest and next nearest carbon atoms. So 2 nearest carbon atom and 4 next nearest carbon atom of the hexagon. So there is a different charge distributed among these carbon atoms of the SWCND. If we dope the uh, uh, sodium and if you adds up the hydrogen molecules on it. So the charge transfer from sodium to SWCND splits over the carbon hexagon nearest to NO. The nearest to that Na or the what we can say sodium. So this is what it says the electric field, okay, which attract the six hydrogen molecules with the binding energy of 0.2611. So this is what a positive charge sodium atom, negative charge carbon atom. So this will try to absorb the more number of hydrogen atom. This is what the you can say the polarization takes place between distribution of charges, which helps the polarization sorry polarization mechanism and which help to absorb more number of hydrogen atoms over there. And the binding energy for this hydrogen atom that we already discussed is 0.26 eV. Okay, and we can have different approximation, that is local density approximation and generalized gradient approximation, and both will show a little bit different binding edges for a hydrogen atom. So the conclusion from this is what the charge transfer first takes place from some charges transferred from sodium to carbon, and there is the polarization which is responsible for the more number of hydrogen absorption on this carbon atom. Okay, this is what the charge transfer. This all the charges, that is 0.579 is mentioned in Coulomb. Okay. So now to understand this, one more property we studied, that is radial component of electric field. To understand the hydrogen adsorption in detail, the electrostatic potential of pure CNT, sodium attached CNT, and hydrogen adsorb hydrogen adsorb NaCNT will study it. Okay, so these are the three different diagrams. One is of CNT, another is of NaCNT, and third is hydrogen NaCNT. Okay, these are the three images you can say, and at the same time there is a electric field curve. This is what the distance in angstrom, and this is what the field around Na, field around carbon, and field around hydrogen. Okay. So the electric field measured and induced by the charge distribution along the outward radial direction of the complex. Okay, the field is moving outward direction of the carbon atom. So this radial component of the electric field from the center of the SWCNT to the hollow side of SWCNT and sodium and hydrogen. So for SWCNT, electric field strength is 8.3 into 10 to the power 10. Okay, only for the CNT, 8 point in 10 to the power, it is found to be 10 to the power 10 volt per meter. And with when sodium get adds up, then it has increased to 29.2 into 10 to the power 10 volt per meter. And if single hydrogen atom adds up on it, then it drops to 24 into 10 to the power 10. That you can check it. Over there it is this value, then it has increased after sodium doping is around 24, and then it drops to this value, okay, around below the 20. So this is what the sodium atom is responsible for the absorption of hydrogen that we have concluded from this radial component of electron. Now this is what the in earlier case, I'll just go back. Here we have only single sodium atom which get attached to the single wall carbon atom. But if you want to have a more and more number of hydrogen molecule to be absorbed on the surface of the carbon nanotube, then we'll first try to increase the number of sodium atom, and on each sodium atom we'll try to increase the adds of the hydrogen molecule. That is done in this to study the what is the maximum number of hydrogen can be adsorbed on this carbon nanotube, that can be studied in this way. Okay, so here now this is what the cross sectional view of a carbon nanotube. So in this you can see 1, 2, 3, 4, 5, 6, 7, and 8. 8 hydrogen atom get adsorbed on the curvature. Okay, curvature of the single wall carbon atom, which is of 80 carbon atom. And after that, now you may ask, like, if we are placing it like this, there is a interaction between two sodium atom. Okay, so it's not like that. We have placed this place the distance between these two sodium atoms sufficiently higher, around more than 5 angstrom. So if it is more than 5 angstrom, there is no interaction between two sodium atoms. On each sodium atom, we are going to adsorb the 1, 2, 3, 4, 5. So we are just going to increase the number of hydrogen atoms, and then we study how it is possible to adsorb this number of hydrogen molecules on this. So on each sodium atom, we are going to increase the number of hydrogen. We try to add some number of hydrogen molecules 1, 2, 3, 4, 5, and 6. So on each sodium atom, 6 hydrogen molecules are possible to get adsorbed. Okay, so with the bond length again same. So even if we have a single atom or we have 8 sodium atoms, then there is no as such change in the bond length. Okay, so the bond length between sodium and carbon is 2.6. That is the range 2.4 to 2.6, and for between there is no change in hydrogen or hydrogen sodium bond length as well, even if we have more number of hydrogen molecules. It can easily absorb this much hydrogen molecules. So like that we have 8 uh, hydrogen 8 sodium atoms. On each sodium atom we have 6, like the total 48 hydrogen atoms get adsorbed on this single mole carbon. Okay, so then how to find what is the weight percentage of the hydrogen. So the formula is like total weight of a system. Okay, total weight means atomic weight. Total atomic weight of system. Which system? Carbon nanotube plus sodium plus 48 number of hydrogen molecules. So total weight of this, uh, and we just calculate total weight of atomic weight of this system, and we also calculated the weight of hydrogen molecule. So total hydrogen molecule 48. So 48 multiplied by the atomic weight of hydrogen divided by the total weight of this system multiplied by 100. That will give the weight percentage of a hydrogen molecule for this 808 WCNT. So like this we studied as we say, discussed 5 SWCNT, 3 SWCNT, 4 SWCNT. So on each SWCNT we try to adsorb this all more number of sodium atoms, and then we try to adsorb more number of hydrogen molecules on each SWCNT. So after comparison, you can see what are the if we have a different CNTs to be used for the adsorption of a hydrogen molecule. So for 33 HWCNT, which can adsorb maximum 36 hydrogen molecule. 42 HWCNT, which can adsorb 42 hydrogen molecules. 50 HWCNT can adsorb only 30 hydrogen molecules. 55 HWCNT can adsorb 60 hydrogen molecules. 63 HWCNT can adsorb 66 hydrogen molecules. 80 HWCNT can adsorb 48 hydrogen molecules. Okay, so here 55 HWCNT, which is the maximum weight percentage 11.2, and 80 HWCNT is found to be 9.2. So the weight percentage is varying from 9.2 to 11.28. So this much hydrogen can be adsorbed on a single SWCNT. Okay, so this is what a good result as compared to the earlier reported result. Earlier they have reported something 5.6, 8.6, and something around 9.2. So here we received around 11.8, which is good weight percentage in this system. So this is all about the hydrogen adsorption. Now, thing is that why we are doing this, why we are adsorbing hydrogen. So nowadays, hydrogen fuel cells and hydrogen cars are developed. So this is what one of the material which is to be used to store the hydrogen atom, and when the hydrogen is released, then we try to dissolve the hydrogen, then it will give the large amount of energy. So this hydrogen can be used as an energy carrier. Uh, so there are basically in hydrogen energy three parts are there: hydrogen production, uh, hydrogen storage, and hydrogen carrier. So this part is useful basically the storage of hydrogen molecule. So this can be used as a carbon nanotube can be used to store the hydrogen. Okay, so because of its porous nature, because of the high surface to volume ratio, this is very suitable material to store the hydrogen as energy. This is what the one part. Another part is what the CNT, another application, that is CNT as a gas sensors. Okay, so here you can check in this diagram. This is again 808 WCNT. Okay, here pure CNT, and that is show the all green color are the carbon atoms, and blue color shown over here, blue color atom, that is again carbon atom only, but we are going to dope, we are going to replace this carbon atom with the sodium. That's why it is just highlighted by blue color. Okay, but it is uh, carbon only. So these carbon atom get replaced. That is called Si dope by silicon. Okay, so this gets silicon, and if you run the program for the geometry optimization, after optimization we got it like there is a little bit bump. There is a modification. The structure get little bit change after we dope the silicon atom. Uh, just replace the one carbon atom by the silicon atom, and this is what the structural change, and this is what you can see four different graphs. The red one, the first red one is what the band structure of pure CNT. Second one is density, total density of state for the pure CNT. Third one is the band structure after doping the silicon, and the fourth one is density of state after doping of silicon atom. Okay. So here you can check, this is what the pure silicon atom band structure is, just little bit modified after doping the silicon atom. The extra state is created in between this. And uh, also, if you see the density of state, this is what the band gap. Okay, so the band gap get reduced. Okay, by some amount after doping of a silicon atom. The thing is that why we are doping this silicon atom. Okay, we can dope any other atom, but we have tested all these atoms, and silicon is found to be more suitable. Now this we want to use as a gas sensor, means we want to detect carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen dioxide. So after this modification, after this functionalization, we try to absorb the O2, CO2, CO, SO2, and NO2. So this is what the base substrate for the gas sensors. Okay. So the SI, this is what the comparison between pure CNT and SI of CNT. So this red color, this is what the O2 molecule. Okay. O2 molecule we tried to absorb on pure CNT, but that was not feasible. It doesn't absorb. The absorption value is very less. So after modification by the silicon, so this atom, the oxygen molecule get adsorbed on this. Okay, with very feasible bond length 1.68 and 1.4. So 1.6 is the bond length between silicon and this oxygen. Okay, it is bonded like this, and 1.460 angstrom is the bond length between carbon atom and this another oxygen atom. So it get easily attached to the silicon atom. So this material can be used to sense the oxygen molecule. The second diagram is what the band structure and density of state for the pure CNT, and band structure of O2 CNT, and this means first this CN2O2. These first two diagrams are CN2O2 band structure and density of state. Another two diagrams are the band structure and density of state of O2 adsorb and SiCNT. Okay. So in second diagram, the band structure DOS tube for the adsorption of CO2 molecule, in which number of partially filled state are observed at a Fermi level, indicating the change in the conductivity of a tube. Okay, here you can see this few. Here we have a peaks, but here we have just the peak get changed. It means the density of state get changed after the adsorption of oxygen molecule. So here the O2 get absorbed on the axial bond of SiC. This is what silicon and this is what the carbon, and this is what the bond between these two. So it just try to adsorb along the bond of silicon. Oxygen get try to adsorb along the silicon carbon bond. Okay. So this forming sigma bonds with the silicon is silicon 3p and carbon 2p atoms. So it forms a bond with the carbon and also bond with the silicon atom. So bond length between them, this is already mentioned, 1.6 and 1.4 angstrom. Let's move to the another CO2 molecule. First diagram is CO2 get adsorbed on carbon nanotube, but we can check the bond length is very high, 3.3 and 3.7. So it is not easily adsorbed on pure CNT. But if you try to adsorb it on doped silicon doped carbon nanotube, then it easily attach. Okay, you can check the bond length 1.7 and 1.5. So this CO2 get physisorbed easily on the silicon carbon silicon doped carbon nanotube, and there is a weak van der Waals interaction between this carbon CO2 and this Si dope carbon nanotube. And this is what the band structure and Day-2 offset for both CNT-CO and Si-CNT CO2. Third one is SO2. This is again another toxic material. This is we try to adsorb on pure CNT and then A side of CNT. So again, you can check the bond length. And these are easily adsorbed, easily attached on this Si-CNT SO2. And there is a little bit modification after doping the CO2 molecule in the uh, density of state. Okay, this is what the density of states for pure CNT SO2, and this is density of state for A side of CO2. So here little bit modification in the density of state as well after the adsorption of this SO2 molecule. Then another one is NO2. So we studied O2, CO2, SO2, and NO2 molecules which try to adsorb on this CNT or A side of CNT. So this is what here this the picture is a little bit different. NO2 can easily adsorb on this CNT. Okay, and if you have, but that is not true for other material. Okay, CO2, SO2, they are not getting adsorb on CNT, but here this can easily adsorb on pure CNT as well. And after A side of CNT, also we have some interaction, strong interaction between the NO2 molecule and silicon atom in this S side of CN2. So here in this case, there is a chemistry option of NO2 molecule, but it occurs due to the hybridization between silicon 3p and oxygen 2p molecules. So this phenomena is completely different. Adsorption of this is binding energy is 2.63, which is a little bit higher as compared to the other oxygen or CO2 molecules, O2 or CO2 or CO molecules. So this is what the first part we discuss is hydrogen adsorption, and second part we discuss is the gas sensors application of carbon nanotube as a gas sensor. Now this is what the few reported results. This is what our inspiration, because this is the pure CNT, the Courier et al. Tried to adsorb this SO2, CO2 at different positions, and they found this binding is little bit weak binding between this molecule and atom with a sufficient high bond length between this molecule SO2, CO2, and carbon atom. So if you modify this with the silicon, then the binding is a little bit stronger, and it can these toxic material, toxic gases can easily adsorb on the side of HWC. That is what the conclusion from our side. This is what the Courier et al. Published in recently 2-3 years back. Then this studied we studied this thing up to the whether it is gas absorption or hydrogen adsorption. This is what is some simulation kind, the first principle study, or you can say using the density functional theory we studied. What are the experimental results? So these are the few experimental um, results or the reported results um, as the applications, other potential applications of carbon nanotube. So the first diagram you can say A, that is IC, okay, SWCNT, single wall carbon nanotube IC. So you can see it is bended, this is extremely flexible SWCNT, and that is we have an integrated chip, and this is reported by Cao et al. In 2008. This is what I experimentally checked. The second is the photograph of flexible nanotube circuit. This is what the electric circuit with the help of carbon nanotube, and the size is 2.5 U, the length is 2.5 U and 3.3 centimeter. Okay, this is what the electronic circuit. These are the two applications in LED. And the third one is also optically image of fully printed backgated SWCNT. So the gates SWCNT can be used as the gates. And the last one is organic light emitting diode with the help of carbon nanotube. So these are the applications shown only in the electronic industry, but these has used applications in biomedical, in curing cancer and all diseases, serious diseases. Okay, so I just added some of them, just only the electronic application of it. Now I use the uh, uh, computation, that is what the custom code to run the program to study the system. So what are the computational details that we required in this? So this I use the density functional theory, which is very powerful method for doing electronic structure calculations. This is based on the principle that all properties of a system of interacting particles can be described by unique functional. So it is density functional theory. So it is the density of a single particle, that is the density, electron density, and these are all in the ground state. So interacting particle can be described by unique functional describing the ground state of the single particle density denoted by rho of r. So here we have all simulations carried out with the periodicity along z-axis. Periodicity along z-axis means the tube is periodic along z-axis. We can extend the tube along z-axis, and whatever we dope sodium or hydrogen or potassium or lithium, that is along y and x-axis. So the repeating pattern will be there along z-axis. Okay, and the dopant are used along x and y axis. So what is the cell? We have kept this or in a cell of 16 and 8.5 dimension, that is angstroms. And the smallest is 2720, that's for smallest, and biggest is 27.4 by 28 by 7.3 angstrom for the largest system. Smallest and largest means each CNT, SWCNT has different diameters. Okay, so if you increase the n or m, then the diameter goes on increasing. So we just change the cell size for that. The simulation cell were taken so that empty space between the nanotube and x and y direction will be 7.5 angstrom. This is chosen because there should not be any interaction between two cells along x and y. Okay, because the cell is continuous along z axis, but it's not continuous along x and y, so there should not be interaction between x and y axis or x and y directions for the CNT. So that minimum distance is taken as 7.5, but maybe more than 7.5 to avoid the interaction between two carbon nanotubes or two sodium atoms or two hydrogen atoms of the neighboring cells. Uh, these are the references that I have used. And one more thing I want to share with you. I'll just show you one. Uh, this is what I wanted to tell you. Now, one more interesting thing. I'll show you the video. So, okay. So this is what I use the Material Studio to run all the programs, and in the Material Studio is just a visualizer, graphic. You can say graphic user interface, and you can model various systems over there, and you can run the program with the help of Cascape or Demo3 and various codes. Okay. So I will show you one. I'll just go through it. Just this is what how you can use it. This is what the view of Monterey Studio, and here you can create a new project. You can name it like carbon nanotube, and can make a one file. This and even just go to the build. This is what I'm just showing how to build carbon nanotube on this visualizer. Go to the build nanostructure, and you can choose n and m values. 1, 2, 3, 4, 5, whatever the values. This is what the 6 6. N is 6 and m is 6. Okay, so the nanotube is built. This is how it looks. Now this is just only lines you can see, but you can change its view like ball and stick and all. That is also shown over there. Now this we went, we can keep it in a cell because in cast step calculation we required the cell and the system is to be kept in a periodic cell. So we'll just going to build the crystal. So you can have various. Uh, you can choose the lattice parameter, that is A, B, C, and alpha, beta, gamma. This is what the cell created, and you can paste this structure in that cell. But there are four you can see, but we want only one, so we'll just choose the another parameter in display style. Okay, and we just set it to origin. Then we'll shift it to the center. Okay, so this is what the ball and stick arrangement that you can change by going in display style. This is what the carbon nanotube, and this is what the 6 6 n is 6 and m is also 6. And then you can shift it easily, and you can keep it in a cell. And after placing in a cell, it will look like this. So cell parameter you can easily adjust. Okay, you can adjust the cell parameter, but without affecting the original structure of the carbon nanotube. And then we'll keep one sodium atom, then we'll keep one by one hydrogen atom, and then we'll keep it for the uh, geometry optimization or energy calculation and all. So you can change the color. This the gray color is the default color, but you can change any color to this carbon atom. Okay. And one more that just one more video is there for you. This is what if you want to run the program. This is what the sample video to run the program. This is what we have a carbon nanotube system. So we go to the uh, cast step tool. Just click on the cast step tool. Move to the calculation part. Here there are tasks. You can go to the geometry optimization. You can go to the energy. You can go to the density density of state. Various calculations are possible. So you just go to density of state, charge transfer, or any other. Okay, and just uh, over there, and there are various parameters to set. So for that you need to study a little bit DFT. Without that you can't learn. But I just showing you the sample program how to run. For the optimization, how to run that. So just click on the run program. So it start running. It start to optimize. Okay, and these are the few files created. That is structure file, then output file, input file, density of state file, or charge transfer, different files, and that you can visualize different structures from it. So these are the videos for us. So that is from my side, sir. Vivek sir, if you are there, then please. Thank you very much for listening me patiently. I think nobody is having doubt. No question. It is there on last slide. Okay, just a minute. I'll just share it. I'll just share it. Okay, so this is an email ID and mobile number. If you have any query, if you have any interest in our field, then we can you can join anytime. Okay, this is my email ID and mobile number. Feel free to contact anytime. Yes, sir. Yes, sir. Okay. Just a minute. Yes, sir. This is what the graphene structure. Okay, so these all are carbon atoms. Six carbon atoms are like a benzene ring. No, six carbon atoms are there in a honeycomb lattice structure. Okay, so it is just a plain sheet of a carbon atom, plain sheet of carbon atom, but arrangement is a honeycomb lattice structure. So it is two dimensional. Means let's say this is x axis, this is y axis. So it is just a two dimensional structure. Yes, sir. Yes. Okay, okay. So I shown at the end the two videos. One is about the software, that is Material Studio software, and in that which code is used, that is casted code is used to run all the programs. Okay, so Metal Studio is a visualizer that you can make a structure, you can run the program on the basis of that, but the code behind it, that DFT code, that is what the casted code. Yes. But thing is that the Material Studio and Castep both are paid. Okay. But if you want to start a research on from your institute, so you can we can have a number of free softwares like Quantum Espresso, okay, or Gaussian. So over there, without any payment, you can start. You just download freely, and these are called open source softwares. So you can start the same thing. You can do it on Quantum Espresso as well.
Any anybody has question? Please ask.
Okay, okay. Link, okay. Uh, and just give me a minute. Yes, yes, yes. I'm just sharing it over there. I'm just sharing the free software link, which is what the Quantum Espresso, that you can easily download from it. So uh, I shared it in the chat box. Okay, please check and note it down. But the Material Studio you can't download without payment, so they will ask for a payment and it costs very high. So better to go for a free software, that is Quantum Espresso, for a beginning. I'm just pasting my email ID on the chat box. So anybody want to contact me, that's on. Sure, sir. Thank you all organizing committee member for giving me a chance to present my work over here. Okay, thank you, sir. Thank you, sir. Thank you very much.